Thanks a lot for having me. And just wanted to have a little bit of credit. This line of work actually started with a grant we received from NSF and the Simons Institute on the mathematical theory of deep learning. It's about 7 or 6 years ago when we're really started at Berkeley and really trying to set out to understand. At the time, the deep networks was very, very popular. There's tremendous advance. And we try to understand mathematically or theoretically what this really means for that. And also another, yeah, Arrow and actually his talk set a perfect stage for my talk. I really love the quote you did in the last, right? If we really understand something, maybe we can actually really understand the nature of intelligence. So this is a talk that I will try to focus a little bit on. And also this is the talk I gave as a keynote at this year iClear. And let's get started. So, there's been a lot of technological advances regarding artificial intelligence, and also there's a lot of misunderstanding about it. Terminologies, different people from different areas, and so the question is, can we understand intelligence truly as a scientific and mathematical subject? Can we actually define it clearly? And the notion about what is intelligence? Can we quantify it? Can we study it qualitatively, right? And towards this end, we really have to go back to some of our scientific common sense, to be honest. Ask some of the very basic, annoying questions, and everybody seems to be avoiding these days, right? Everybody claims they're doing general intelligence, super intelligence. What is it, right? Why in the world do we want intelligence? Why? Right? Everybody talk about machine learning. Why do we want to learn? Why, what's wrong with doing nothing? Right? See, then the question is that once we understand the purpose of it, right, then maybe the rest of all the things, the different variation of networks, it just means to the end, right? And they're just manifestation of something towards the same goal, right? So maybe that's right. Then we can worry about how can we make it correct, make it optimal, make it efficient, right? This will become natural. I love the quote from Richard Feynman, right? But if we cannot create something from first principle, I really don't understand it. Right? The question is, what is first principles? We all know, right? The universe was governed by laws of physics, right? So what did the quest of understand physics? And there's a movie called, A Theory of Everything. Well, not quite, right? Maybe the physical world, the theories of physics is enough, but there's something actually against physics, right? The life. We also need a theory for life. To me, turns out probably the mechanism behind life is intelligence, right? The theory, the principle of intelligence is governing the evolution of life, right? I love this quote from, right? It will reflect a lot about what we said today, and also what Eric has said. Just as the constant increase of entropy is the basic law of the universe, so is the basic law of life to be ever more highly structured and struggle against entropy, right? So for that, let's just understand a little bit about the beginning of life, right? The intelligence. Right? I will skip some of this for time of interest, right? So DNA is the first pre-trained large models, okay? You try to store the knowledge the species has learned up to that point, use a very special code, which amino acid, right? And then encode genes. The knowledge was encoded as genes and so on. That's how the knowledge, and even how it evolves, random mutate, selected by nature. It's reinforced learning by nature, right? But very primitive. Yes, things evolve, things advances, but at a huge cost, very unpredictable. Sounds familiar? Sounds very, very familiar, right? But then later on, something magic happened. That evolves about 3 billion years. At some point, right, neural systems start to appear. Senses start to appear about 500 million years ago. Then after a very short period of time, there's an explosion of life, right? What has changed? We have a new code book. Our neurons be able to code memory for individual animals now. They can build their own memory in addition to what they inherited from their parents through DNA. It's different code book, different set of knowledge, That's brain. That greatly enhanced adaptability of individual lives, right? Hence, there's called the phylogenetic intelligence is that individual doesn't have intelligence. Species have. They evolve by natural selection. And once you have a brain, have a neural systems, individual ontogenetic intelligence means that everybody be able to develop its own memory, be able to acquire new knowledges in addition to the DNAs, right? Evolves much, much faster. Actually, with the more advanced life form, you notice something very simple, right? More advanced life form or intelligent form, the longer you stay with your parents after birth, right? My 2 kids are still with me, right? Like 18 years, for God's sake, that's a lot of work, right? Why? Think about that. Then later, something interesting happened with human, right? Human early on with human life, we start to become a social animal. We start to develop our language, spoken language, even better, written language, meaning that we significantly increase how we share information, that the knowledge we learn, and also be able to pass it on to our next generations. That replace the role of DNAs, right? But a different code book, store different set of knowledge, evolve in a different way. Finally, about 3,000 years ago, we don't know quite how that happened, right? Philosopher, mathematicians start be able to develop something abstract and be able to develop very different mathematics, different language, the language for science. And even how it improves the mechanism is also different. Scientists be able to generate hypotheses, proactively explore the unknowns now. No longer just to summarize knowledge in a very empirical way. So 4 different stages of intelligence, 4 different types of code books, 4 different types of knowledges, 4 different types of mechanism to improve. Keep that in mind. That's a background. Of course, these days everybody say, I mean, this just drives me crazy. I love history, but then, all the young generations, guys, get the history straight, okay? Right, the study, I mean, everybody say artificial intelligence started in 1956. Absolutely not, okay? Meaning that if you say that, you're amateur, okay? The magic era that the people are just starting, trying to understand, to make machine imitate intelligence started in 1940s, right? The guy you should remember, Norbert Wiener, right? He started the program called the cybernetics. In fact, it's under his influence, people started to understand different mechanisms, necessary mechanisms in the intelligence systems, how to install information. His student, Shannon, developed his information theory. And he studied how information can improve, feedback, error correction. That's the foundation of system theory. And how, under his influence, there's young von Neumann actually developed how actually intelligence improve the decision making to make their decision better, prediction better, game theory, right? In fact, von Neumann actually credit Norbert Wiener for the development of his the architecture, von Neumann architecture for computers, because he wanted to design a machine can actually carry out the mechanisms for cybernetics, okay? And only after the 1940s, 1950, Turing asked the question, can we separate machine and human? Because you can see all those mechanisms is about to study animals, how memory, be able to perceive the world, build a memory, and use it to predict. That is a common mechanism uniform to all species, right? Animals and human. And Turing started asking, then what's special about human? That's inspired later, artificial intelligence. We'll talk about that a little bit later, right? Let's stay with this level of intelligence first, right? Machine intelligence, and try to imitate animals. Of course, people didn't know where to start, as usual. Whenever we didn't know how to start, we look at the nature, right? We learn, how to model, understand individual neuron, how it works. That's actually Warren at the Water pits. Actually, Water was a postdoc of Norbert Wiener at MIT. Was also under his influence to study the mathematical models of neurons, right? By the way, everybody know what's the Wiener is famous for in the signal processing? Wiener filter. It's denoising, okay? Don't forget about that. Right? Then, of course, People get a little bit obnoxious whenever they think they understand a little bit about nature. They start building all the machines, collecting all the neurons together, build the perceptron, right? They spend about $6 million, which is kind of equivalent to $1 billion these days, right? Of course, it didn't work. Then people get a little bit humble, say maybe we didn't know something about the neurons or how the brain works. In 1980s, inspired, Fukushima and Yanakun, look at that. Maybe those neurons they're not arranged in an arbitrary way. They're not collected in a random way. They have patterns, right? So that is inspired convolutional neural networks. Right? And this is kind of history, right? We go up, we discover something, we get a little bit obnoxious, then we hit a wall, we learn from the new natures again, and so on, back and forth. So we also understand the mathematics a little bit, and so on and so forth, right? This is kind of history people knows. And more younger people knows, most of the younger people only know this part, right? On 1912, there's the 2012, there's Alex Lett and so on and so forth. And there's also generations of neural networks, right? How they evolve resemble very much like early stage of life. Very primitive, right? Random primitation, everybody try. Some good ones survive. I won't even mention how many didn't survive, right? The guys, remember there's AutoLAS, AutoML, right? Any of those go, at that time, people think they can discover all the things in the world, right? We never heard about them anymore, right? I mean, it's like this. I mean, it's reinforced learning, right? And yes, it improves, evolves, but at a huge cost and very unpredictable. And in the end, you get black box, just like our DNA. So still things we don't understand, right? And hence, this is to a point, right? Maybe at this stage, right? This is about 80 years ago, it hit me, right? Maybe it's probably high time to, can we really, this kind of, yes, it works, but it's very hard to explain and impossible to have any kind of guarantee. There's hallucinations, safety, you can, of course, you can do all kinds of band-aid, like fix the data, fix the, security, cost to improve. So, right? Can we develop a principal approach to this? The question is very simple. Asked very annoying questions, right? You try to avoid. What the heck we're trying to learn, right? And then how to learn it. Then how to make it correct. Very, very simple. Can we make it this is a scientific, mathematical, computational problems, right? This is our attempt. Well, why do we need intelligence? Why do we need to learn? Maybe the world is not entirely, yes, the second law of thermodynamics says the entropy increases, but we're not there yet. We're not at the end, right? That end of the universe. So the things are still not entirely random, and it's still largely predictable, right? So hence, either intelligence in an empirical form or science is really trying to learn what's predictable from the sense data of the external world. Every animal is Newton. They have learned how gravity works. Dogs, if I throw a ball, can catch it very quickly. Although it doesn't know the equation. They read it in a different code book, right? They learned the trajectory, how things fly. Probably better than human, faster, right? But not in the written in the differential equations. Works the same way. Now the question is, if this is what can we actually make this mathematical? What is the uniform mathematical problem behind learn something predictable then? Turns out, yes, you can. Mathematically, all predictable information is encoded as a distribution of low-dimensional support in observed high-dimensional space. Very simple. Newton's law, first law, right? If a particle does not have any force, travels on a straight line. Doesn't appear randomly anywhere in the three-dimensional space and time. Okay, that's make it predictable. Stays on a one-dimensional straight line. Make it very predictable. Of course, more complicated data, images, our touch, senses, hearing, maybe slightly more complicated, okay? Then maybe a subspace, maybe mixture of subspaces, mixture of manifolds, right? Nevertheless, they're low dimensional, right? To me, this is the only inductive bias ever you needed, okay? Nothing else, right? Can we derive everything from this, right? This is inductive. Everything else has to be deductive. This is the first principle. If we can start from here, can we derive everything? Well, let's collect a little bit, right? This is, for example, what's low dimensional helps us to do? Completion, right? If I only see a partial observation, just like Eric said, we can complete images, complete the next sentence, next world. That's just what it is, okay? Or we have noise observations, right? If we know the underlying structures, we precisely, just Eric has given an entire beautiful lecture about it, we can do the empirical Bayesian, right? Allow us to denoise, get the natural images. That's what we do, right? Against the structure. And of course, what we see very corrupted, errorless observation, they even against the low laws. Oh, something's wrong with the apparatus, right? We do robust estimation. We recognize things despite occlusion, despite conclusion. The prior is that you know the structure of the data has to be low dimensional. You get a hold of the structure, low dimensional structure, you can do very, very robust inferences despite corruptions. Before that, nothing is robust, okay? Renal filter, Kalman filter, all this empirical Bayesian, everybody is doing the same thing, okay? Nothing else. So now, can we agree? If we agree, this is the only inductive bias we're going to use, right? Assumption we're going to use. Identify a distribution with low dimensional structures from sense to high dimensional data and transform them to a compact and structured representation. That's it, right? If we set this as a goal behind all the learning, how do we do it? Can we derive everything from here? Well, yes, we can, right? If a distribution with low dimensional structure, how do we measure it, right? How do we measure that? How do we pursue it, right? Those are low dimensional, hence the entropy. Well, think about it if you're not familiar with, entropy is kind of volume of distribution, okay? Of the underlying data distribution should be very small, actually zero, right? So we'll deal with that a little bit, right? So if it's a discrete entropy, we sum them up. If it's differential entropy, we take integral, right? They're kind of like that in a very big space where they really are very, very low dimensional, very highly low dimensional. Intrinsic dimension is extremely low compared to the ambient space. That's it. That's intuition. Actually, Shannon actually studied how do we measure the information content in such a distribution, right? Then how do we pursue such a distribution? It turns out it doesn't matter if it's high dimensional or low dimensional, right? I mean, the principle should be the same, right? Imagine, I love the approach, right? I mean, this is just to use a little bit the scientific training, okay? Just do a little bit thought process, thought experiment. Imagine you're a creature living in a one-dimensional space, right? You observe some things, right? But nevertheless, the world is structured, meaning that there are some laws, underlying laws governing the observation, but you see something noisy. You try to discover that, right? So those are all the possibilities, the probability that things shows up, X shows up, right? So you can guess, maybe the law is just 2 lines, but how do you discover that? The creature only observes those random noisy X. So what do? Try to guess maybe every little X come from the direction where the probability is higher, okay? Push them a little bit. Maybe this comes from that way, because the probability is higher that way, okay? Do that. Do that iteratively until the distribution converge, right? Voila, you say, oh, those are the 2 peaks. Then you can write an equation, right? Equation, basically one equation reduces the dimension by 1, you get 2 solutions, right? You will be the Newton of that world, okay? One equation, reduce 1 dimension. Remember, see, all the laws, right? People discover something interesting, right? There's except the 1 law that is the inequality. The rest are all equations, right? Except the second law of thermodynamics, entropy increase. The rest are all equations because 1 equation reduces the dimension by 1, another one, another dimension, another one, another dimension, right? It's all about chasing that underlying structure. Even physics, science is doing that, let alone intelligence. Now, let's look at this general process. I mean, the Eric has said there's a lot. See, if the universe diffuse, right? The noise, everything bounds. So you take some noise, add it to your distribution. You can actually easily show the entropy of this process increase. It's a simple exercise, right? But this is a lot interesting, right? This is what the physics care about, right? The world is. We care about the inverse, right? We'll fight against entropy, right? We want to denoise to discover the underlying laws despite noisy, corrupted understanding. Can we take the noise? Turns out, well, let me know. We were writing a book. I was trying to find out. I actually found that nobody actually proved this, right? Turns out this process actually the entropy decreases. I couldn't find anyone prove this. We give a proof. If anyone know a proof for this, let me know. Okay. So basically, actually prove under this continued process, you do the denoising, the entropy of the distribution always decreases. Differential entropy decreases. Let me know if you know a proof. At first I thought that someone must have proved it. I looked everywhere, including my students. We couldn't find it. This is almost a very intuitive result, but actually the proof is a little bit technical. Okay, it's not that obvious. But nevertheless, you can do this. You can converge. So if you keep doing this, you end up with the random noise. You can get the natural images, right? You can learn the distribution of natural images or text and everything this way. But how do you do this, right? As Emma actually said this, right? This thing is interesting, right? This thing, we actually don't know it. We only have samples of this distribution, right? We don't know the forms of it, right? We only have a finite samples from it. Turns out, I mean, what the heck it looks like, right? What is it? We don't have this distribution P. How do we realize this? Well, if you believe, right, this library, you know, if we believe this is well, we just be bold. I mean, neural networks kind of everything. Let's just do a transformer or grab whatever you have enough samples to fit the neural networks. That actually works, right? But this is not very satisfying. Why? It has this done. Is this thing redundant? Right? Anything unnecessary? We don't know. Why the heck has to be this? Right? How do we improve it? Well, we actually sort of know this, right? I mean, in fact, the whole history about the denoising is doing this, right? I mean, some special form, many analytic history study, PCA, ICA, GPCA, sparse coding, all turns out it's doing this, okay? Because with those, if you know your data lying on a mixture of subspace, low-dimensional Gaussian, this actually gives you a very explicit form. You can write them down, right? Softmax and also the subspace projection, right? What this looks like, this already looks like a primitive transformer, attention head, okay? That's what it is. So basically, if you have any arbitrary distribution, you just approximate, no piecewise linear, just like Errol has said earlier, right? And then all the operator just to do the denoising for you, project out those local subspaces, nothing else. And this is explicit, right? So what about a more general distribution then? First of all, how do we pursue that? Right? How do we build explicit representation? Even the denoising process, you can say, it gives us something empirical or something implicit to sample from against. But what it looks like, for many of our purpose, we want explicit coding scheme, right? How do we get an explicit representation of distribution with low dimensional support? And this problem actually troubles me about 5-10 years, about quite a few years, because see, if we try to model distribution, when Renee and I were studying the GPCA, right? If our data lies from the mixture of subspaces, but the measure, how do we separate models that all dimensions, the volume is zero, right? A mixture of 2 subspace, 3 subspace, the measure are all 0, right? The differential entropy are negative infinity. How do you compare negative infinity against another negative infinity? Which one is smaller? Right? It's a technicality, nevertheless troubles us a little bit. So it's about early 2007. We actually realized that. So you want to have explicit coding book, and you actually can never represent the continuous distribution. You have to sacrifice, right? You can only count on the noisy encoding and decoding scheme. Actually, that was the idea from Shannon. That's what's the basis of coding theory. You quantize the dimension. Right? How do you quantize? Very easy. You pack the space or the distribution of interest with epsilon balls, cover them, right? Sphere packing, and then count the balls. The center of the balls are exactly the code book, right? So if you know nothing about the space, nothing about distribution inside that space, you just have to pack the entire space. You get a very large, long coding book, right? The coding rate will be huge. But if you happen to know where the distribution are, you only have to pack them with the green balls. The number of balls is much smaller. You get a much compact coding book. The average coding rate will be very big. So this is about going from the ignorance, right? If you know nothing about the distribution, the ignorance to the knowledge where the distribution is. You through compression, right? But the compression itself is not enough, right? You also want to organize it, make the correlated things uncorrelated, maximize the overall rate to the knowledge. So we call this rate reduction. So basically, you can think all the useful things measure the information gain is relative what you don't know, right? If the space, the ignorance, so you know the distribution. The difference is exactly the information you gain by knowing where the distribution are in the unknown space. And also that corresponds to the coding rate or coding length reduced by knowing that distribution. Right? So it's actually a very universal measure. Right? The only thing you can control is the size of epsilon ball. Okay? So the precision, how you want to encode your data, right? Well, these days, a fancy name is tokenization, right? So that's really, so this is actually objective. You try to maximize, right? The ignorance and the knowledge. The difference is the information gain you have about the world. Then if you approximate your data as a mixture of Gaussian, you actually can write this down explicitly. Everything becomes analytical. Right? The whole and the parts, the ignorance and the knowledge. The difference is the gain, right? Then, of course, this looks like a little bit complicated, right? Nonlinear function log determinant of some covariance, right? Nevertheless, how do you optimize it? We can actually, in order to find what's the best representation, right? Going from here to there, we can do this incrementally. We can just take the gradient. Everything I said today is calculus. Okay, you don't need any advanced mathematics, right? This is multivariable calculus. You take the gradient and look at what the operator looks like, right? This actually looks like a ReduNet, right? And also mixture of expert. It's actually the softmax here. This is actually exactly the parallel channels, different subspace, and encode the different clusters. Right? This is what we did a while ago. It's called the ReduNet, try to reduce the coding length. And it turns out this looks like a very horrendous, object function, right? Turns out this function has something to do with the mother of all inequality, right? Lib inequalities. So actually, this object function actually has a beautiful landscape. It looks very complicated, right? But turns out that we did some analysis. The maximal global maximizers always corresponds to, orthogonal subspaces, this configuration, always, if you can get the global maximizer. And turns out all the saddle points are regular. You'll never get stuck on even if you run gradient descent. And also all the local minima maximizers also corresponds to orthogonal subspaces. You can actually do that. Very, very beautiful landscape. Basically, you can actually find this kind of representation, just run gradient descent, layer by layer, right? And this is not just right yet, right? So we get to this. This just make the different subspaces incoherent, but this is not sparse, right? Because this subspace does not align with this axis, right? Just like Eric said, if we want to make the representation sparse, we want to, so for example, we want to only, if I say apple, orange, right? I only want one neuron to fire, X2 to fire, not the two neurons fire simultaneously. So this is a much more sparse in terms of physical realization. So you want to make your representation align with your axes. Just add this sparsity term to this rate reduction. Again, we do the same optimization, right? This is the object function. How do we do that? Just do gradient descent. Compute the gradient of such object function. Of course, I mean, since this has 3 terms, many methods you can do, right? How to do gradient descent for such object function? The 300 years of gradient descent, guys. Design all algorithm you want, right? So we just choose one. This is we do compression first, then the sparsification. We do compression step and alternating minimization, right? This is just exercise for people to do optimization, right? Just compute the gradient, what they look like. That's what you get. Compression terms look like this. Remember this mixture of subspace thing? from ICA, PCA, GPCA, sparse coding, they all look like the same, okay? That's what it is, right? Do the compression, then sparsification. Well, just take the simplest algorithm, right? Lista, Yang actually worked on this a while ago, right? Just to learn a sparse code and to simplify it, right? To sparsify it, there's 2 steps. And you get something very similar, right? To something, right? You know. And turns out, right? If you just stack, this is a greedy descent, 1 layer at a time. Just stack them together, you get a deep network. And every layer, you know exactly what it does, right? And there's actually, this is a layer-wise. Each layer is exactly greedy descent to optimize the coding rate. Compress, sparsification. That's the individual layer. The whole network, there is actually beautiful explanation, right? Just like Aaron actually said. The forward, once you know the codebook, once you know where the sphere packets are, you just use them to denoise, compress, denoise against the codebook. Okay? But what if the codebook is not optimal? Remember, DNAs, our brains, language, and mathematics are different codebook. How do you know for the certain type of knowledge which is the best codebook? You have to optimize it. You backpropel track. So you actually use any task, supervised, unsupervised, whatever task, to optimize your codebook through various optimization mechanisms, RL, feedback, whatever knows. You optimize your codebook and use it. Forward is always denoising and compression. Backward is always learn the codebook. Okay? Everything is completely explainable. So hence you end up with something fully mathematically explainable. And it turns out, see, you can see this is actually similar to this one, right? But this is the most basic derivation, okay? We have not used any advanced gradient descent yet. Preconditioning, conjugate gradient, acceleration, nothing has started yet, guys. This is the most basic derivation. It's already better than this, okay? Because you can learn not only everything is mathematically explainable, and also the semantically different heads start to learn statistically and geometrically meaningful structures. They pop out, right? Every subspace, they're attended to legs, bodies, faces, and ears with no interference. They just learn, they just compress. This is the best code learned from this data set. And you can see, as I said, things just get started, okay? Once you know each layer is just doing the optimization, optimizing a clear object function, you can start to optimize. The same network also scales, right? And also the attention part, remember, it's quadratic, right? Everybody, you know, turns out this is what I clear this year. Turns out that's not necessary. Just take a variational form. Once we know this object function, we just take it, you know, if we just do a variational form and design a better gradient. And that complexity is actually can be linear time complexity. This is the first time you can derive mathematically, right? Linear complexity attention head. And also, is this looks a little bit weird, right? This MLP layer, it's very too generic, right? Why do we slap a MLP in between the layers, right? It's very, very generic. Why do we need a very general linear transformation? Must be doing something, right? Is that necessary? Turns out it's not. Actually, you can actually get rid of it. You actually can prove the same structure, do the denoise and compression with the same convergence rate, okay? At least theoretically. Right? So you actually can make it much more compact. And also, once you have, now we know the objective of learning, right? We compress what's similar, contrast what's dissimilar, right? You can actually rewrite a lot of things. This is the work with the, Syn Dino we just did, right? So this is the previous pipeline of Dino, highly engineered. This is all the hyperparameters, right? All the red part you can actually remove. This is a new diagram. The object function is much simplified, just using a code rate regularization. Right? You get a much more simplified diagram and get rid of 10 or 20 hyperparameters. Extremely simple, and also performance is better even. Very simple, like that. Right? And so for the first time, right? And no more trial and error to design better network architectures. I actually can claim that. Right? The design better network, we have not started. There's 300 years of design better and better gradient descent. Not ideas has not even tried, okay? Preconditioning, conjugate gradient, and all the acceleration, okay? Guys, right? But at least the objective will become very, very clear, right? You try to maximize information gain. They're just the operator are just doing the optimization, that object function, optimizing the object function. And what you end up with, if you learn an object function correctly, you have enough layers, iterations, they converge to equivalent subspaces, dictionaries, optimal dictionaries. Now, well, this is just one way to compression, right? To pursue the gradient, to pursue the distribution. But do you necessarily end up with the correct one? You never know, right? How do you know you're not losing anything, right? From here, how do you know you have enough data to cover the distribution in the first place? You never know. The only thing you can know is that you use it to predict. You use what's in your memory, you currently learn to predict whether or not that match with the observations, right? Hence the autoencoding. One question is if the memory might try to estimate my current based on my current memory, current learned distribution here, I try to regenerate to predict if the distribution match or if individual samples match, right? To some extent, right? Hence the notion of autoencoding. This is the only way you can actually check if your distribution has learned correctly. But now, once you know that the autoencoding is doing this, how to do the autoencoding? Just exercise, right? Before, remember the max autoencoding timing actually, guessed what the encoder-decoder looks like, right? They are not even symmetrical. Turns out that that's completely unnecessary, right? We know the forward process is denoising, the other one is denoising. Then all you have to do, and we know that architecture, the only thing you have to just flip the sign. One way is to remove the noise, the other one is add the noise back. Nothing else, okay? This is like exercise for students. And we did this a couple of years ago. It works. Actually, it works even better than the original one, right? So everything becomes explainable. Well, is this so somehow we are basically trying to learn, right? We have a distribution, we try to map it to our internal, and the z we try to reproduce, get the x hat. We want to make sure they're the same, basically, right? Has something to do with Philip just talked about. I mean, how they're similar. It's my memory. But of course, we say, okay, we try to correct the error, right? We try to correct the error here, right? This is what we try to. It says if there's any error, we feel like maybe we want to improve our distribution estimator, right? Make sure our distribution is improved. But keep in mind, the nature does not even have this option, guys. Right? This is very odd. People don't think about how they train the data, right? Nature doesn't have this option. We never actually measure, right? What are estimated in the world is the same physically, right? That clock is wrong, right? We know it's perfect circle. Have you ever measured? Do you carry a ruler or compacts in your pocket when you grow up? Animals, never, right? When the tiger approaching, oh, stop. I wanted to check your distance and speed, right? I'm still young, I'm still learning, okay? You don't have that option. How in the world do you learn a representation of the world without actually physically have this option? Unlike the engineered OpenAI, right? We control both ends. If Z is something wrong, we penalize it. X is wrong, we penalize X. Nature doesn't have that option. Nature learns everything in the brain. Can we learn the predictive model? Can we learn the distribution of the data in the world correctly? Just doing everything internally? The answer is yes. The one assumption you need is that the distribution you learn in the world is precisely low dimensional. And if your network has enough capacity, you can actually learn everything just to correct an error in your internal representation. And this is something known to Wiener 80 years ago, okay? This is very much a basis for feedback control. You do things in a closed loop. So all intelligent systems in nature are closed loop, correct the errors with the feedback. Then why everybody is yelling, we do end-to-end, okay? Right? It's ridiculous, right? This is against the scientific facts, right? Common sense, right? We do everything. So we, as a control engineers, we're trained, right? Closed loop, open loop system is always for a closed world, no matter how big. Closed loop system is for open world, no matter how small. Okay, remember that, right? So this is a lesson we learned a lot. Also, there's a lot of things that were, how do you make this closed loop system to work? right? To make sure that this difference, correcting this errors here, actually, after this error is corrected, there will be no error in the x-axis hat. How do you do that? This is actually, you have to use a game theory. You have to play a game, constantly proactively see if there's error in the perceived, predicted errors here, right? So this is actually some work with students actually from Yang Kun, and we played with this idea a couple of years ago. In this closed loop system, the basic conclusion is that you can learn things continuously, even sample by sample. And this actually can learn very efficiently. Even a sample, a couple of epoch, you actually can learn the distribution, just looking at one sample at a time. And so we all know open loop system, if you retrain it, there's a catastrophic forgetting. These days, people never talk about it when they train large models, right? They just don't look at them, as long as they do very well in benchmarks, right? But it's still there. We have a paper about it, right? So, but a closed loop system, if you learn gradually, incrementally, it does not forget catastrophically. It actually forgets very gracefully, right? Just like our brain. And turns out that just just echo a little bit some of the earlier talks, right? I mean, it's probably time to learn from nature again, right? We're already getting diminishing return, guys, right? Elon Musk spent what 10,000 GPUs and got a 1% improve, right? So maybe it's time to look elsewhere, right? And then sparse coding, subspace embedding, predictive coding is everywhere, right? In our internal, this is actually from the IT cortex, right? How the monkey brains organize different object categories of objects, right? Just like orthogonal subspaces, right? And this is also a paper I did. There's nothing else to do during the pandemic. So I wrote some position paper with Doris Chow and Harry Shang. And the principle, we think that behind the emergence of intelligence, pursuing the simplicity, and do this in a self-consistent way. And then there's a lot of questions, how neuroscience verify this, how to achieve self-consistency, forward optimization versus backpropagation. Nature cannot afford backpropagation, right? Even Young recently, the Hinton actually recently admitted that, right? Nature used different mechanisms to correct error to learn, right? And closed loop versus open loop, right? And everywhere here is closed loop. Why everybody yelling and we do end-to-end, right? It's kind of odd. So also, people talk about, right? Big models are, compressing data. Compression is a very loaded version, right? That actually takes a human 80 years to realize how to implement, right? So people say, big network models are optimizing complexity. That's actually nonsense, okay? Right? It takes about 80 years to realize that the very contribution of Turing and Shannon is that what is computable, what is implementable, for God's sake. Okay, even what is computable is not affordable, right? There's NP hard problems, right? The only polynomial time you have a chance, but can you also afford a polynomial time algorithm? So no, you cannot. Anyone still use Newton algorithm these days? No. Why? Because DNA and the BP are more scalable, right? Something you can afford with 1,000 GPUs, okay? But does nature has 1,000 GPUs? No, absolutely not, right? There's at least 10 magnitude separation of efficiency there, right? They use different mechanism. Hence, they must be using different architecture that will enable different optimization mechanism to learn the data distribution, to build memory, right? So from all the multiple senses, how do we build a model that learn the internal structures, low-dimensional structures, and build our memory for that? And on top, there's a tiny little bit of that worth sharing. We encode with languages. Okay, so every time this says language is a modality, no, language is not a modality. That's completely wrong. Okay, language is a code book. We learned to encode our internal representation of knowledge. Okay, it's not a modality. It's a code book we learned. Right? It's a fraction of things. Right? There are parts in our brain we learn we never have to share. Okay. Also, you don't want to know. Right? So hence, look at our cortex. Right? Our cortex actually organized in a very, very different way. Right? So these days, everybody says we build a big model, end-to-end, train it, pre-train it. We solve all the problem in the world. Right? Well, it cannot even learn itself. Right? If there's anything wrong, it cannot even know what have memorized correct or not, right? It's not even closed loop. And is one loop enough? Absolutely not, right? The nature has a very different architecture. Like a mouse, right? Their cortex is very similar to human. We actually scale them up. The areas gets large. So it's not like we against the scaling laws, but we want to scale the right thing. The nature scales the right thing, right? That is highly, highly efficient, right? So how do we organize this, right? So it turns out probably every loop, every autoencoding at every stage is just maximize organizing information, maximizing information gain. You know exactly what you gain by adding an extra layer, adding an extra autoencoding to it, right? So now everybody these days talk about what is general AI, right? I said asked multiple times on Twitter. Can anyone give me explanation? Give me a definition. What is the general AI is? Nobody did, right? So turns out that they are confusing two things, right? Knowledge and intelligence, right? Knowledge is never generalizable, no matter how much you memorize. Okay, knowledge is only generalizable, applicable to a closed world, right? Even science is falsifiable. Okay, so but the ability to learn, that's generalizable, right? So hence, intelligence is one has the mechanism to self-correct, self-improving existing knowledge. So in very, very mathematical terms, right? Knowledge is actually the integral of intelligence behaviors mechanism. Intelligence is actually derivative. If we forget about valuable lesson in history, collectively our intelligence is negative, guys. Right? So you can ask this question, right? GPT, which one has knowledge, which has intelligence? The answer is obvious. Okay, once you know the answer. If you look at the things from the right angle, a lot of things are very simple. Right? So now to summarize, right? Look at the history of intelligence in nature, right? Phylogenetic, ontogenic, societal, artificial, right? What's the difference? What's common? They're all using different codebook. They learn through different mechanism, right? Codebook. Alice, neural networks, alphabet words, and the mathematical logic. Information, what they encode. Genes, DNAs, memory, natural languages, and scientific facts. How do they improve? Reinforced learning, right? Continuous error feedback, trial and error, hypothesis testing. Okay, very, very different, right? But similar optimization. 4 different type of codebook, 4 different type of knowledge, different types of mechanism to improve. So now let's look at the AI program, right? 1956. Everybody say we're AI era, right? Last 10 years or decade, we're doing AI. Well, I really encourage young folks to read the history, okay? Nobody does these days, okay? Everybody get the facts from Wikipedia or from social networks, right? Look, this is from the proposal. Attempt will be made to find how to make machines use language from abstractions and concepts to solve kinds of problems reserved for humans and improve themselves. Now let's look at not the problem we try to solve, just look at the mechanism people have implemented, right? So what is similar? Today's AI, what is the problem? What is the mechanism? Denoise and compression, object recognition, image generation, text generation, reinforced learning, compared to what the animal intelligence has, right? Signal processing, information representation, prediction, error correction, optimal control, game theory. That's 1940s. In fact, we have not even implemented the mechanism revealed, discovered in 1940s fully in our current AI systems, right? So-called AI systems. And we really have not studied, right? The things that are unique. What is abstraction? The first thing my student test, every single big model came out. Does the model understand natural numbers? The answer is absolutely no, okay? That's it, right? Then how in the world, yes, it solves Olympia mathematical problems, but there's a difference between memorizing something against understanding something, okay? We are all scientists, we actually know that. So we haven't restarted, right? Causality, hypothesis, informing, testing, problem solving. We actually don't know what happened 3,000 years ago in our brain, right? So maybe it's time, right? I mean, this day as a scientific community, probably we have failed, right, in the past decades or so to formalize our problems, right? Also to evaluate the results from industry with all the technological advancement, right? to separate something very simple. What is memorizing against understanding, right? The system can self-learn or not, right? Can the serialize to gather information to explore exploration in a very active way by serializing, right? The form of hypothesis, do experiment, and do deduction, right? So what are those systems, right? So everybody said we do Turing test, right? Actually, Turing test is fundamentally flawed, okay? Because it's just guideline, okay? Right? It doesn't have, it's not implementable. The one problem is that say this is a human to evaluate. Which, who, you or me, right? What set of questions we should ask? What is the conclusion? When the conclusion can be scientific, rigorous, we don't know, right? We have to replace with something, a scientific procedure, so we can test if a machine or human truly understand the knowledge. Right? And also, at first time, right? Even animal and the machine, can the system, the current machine, current models really can have self-learn, correct the memory in learn. I call it the Wiener test, okay? That's what he proposed. And the Turing test is between human and machine. And also maybe the next stage is, can we separate machine and a scientist, right? The behavior of a scientist, I call it a Popper test. Scientists serialize things and deduct, check if the result is consistent, that's mathematics does. If the theory is self-consistent, that's mathematics does. And the physicist or scientist does is to check if the theory align with is consistent with the physical world, right? To do hypothesis testing, evaluation, to do experiment. Well, there's a long way to go, right? We barely scratched the surface of intelligence, to my view, right? But there is a chance. Now, I think there is a hope to develop, right? To study intelligence truly as a scientific, as a mathematical and computational problem, right? What to learn, formulate formally, quantitatively, what to learn and how to learn, and to verify what you have learned is correct or not, if your method is optimal or not, right? So I like this quote from Einstein. This is a quote he says about science. Everything should be made as simple as possible, chasing parsimony, but not any simpler, self-consistency. Okay, against it. It's exactly this one sentence says the two principles behind science and also behind intelligence. Right? It took us about 8 years to collect the theory, mathematical and also experimental evidence, so that to build the framework, right? We're actually pushing out, there's a manuscript with my students and postdocs, and how do we learn deep representation of data distribution? That's a common problem that Eric also talked about, right? And how do you explain everything? I mean, this is truly, again, as I said, this is actually supported by Simons Institute. I'm very, very grateful. And that is really a university multidisciplinary effort for academia. So these days, a lot of young researchers think that they're really disadvantaged, right? They don't, I mean, it seems that if they don't work with industry, there's nothing else they can do. They don't have the data, they don't have the compute. They forgot one thing, they're wonderful problems for them to study, okay, in academia. These are far, far advanced, far, far more deep, far more complementary to what being practiced in industry, right? We barely started, okay? We scratched the surface of intelligence. There's a long way to go, right? Just all you have to do is understand the history a little bit and learn a little bit of mathematics. So that's all. Thanks.